So welcome to my 6th lecture series. So in the last class you have learned the Stark-Einstein law. Okay, so Stark-Einstein, I just recapitulate once again that the Stark-Einstein law says that if any kind of photochemical reaction takes place, then the number of molecules reacted should be equals to number of photon absorbed or number of quanta absorbed. Or in terms of molecule, if we replace a moles concept, then number of moles reacted per unit time should be equal to number of Einstein absorbed. Okay, so there are some limitation of the Stark-Einstein law also. Okay, so the first limitation is the law of photochemical equivalence is applicable to primary process where one molecule get reacted by absorption of one quantum energy, but it is failed in such kind of reaction where more number of quanta or photon of energy are required for one molecule to react. I'll discuss one by one more elaborately. For example, you just see the corresponding reaction of polymerization of anthracene into dianthracene. So this kind of reaction takes place in presence of light, or more precisely we can say this reaction can take place by the ultraviolet light by absorption of two quanta of light. Why? The question is why the absorption occurs by two quanta of light? Because if you see the reaction, two molecule of anthracene, it basically absorbs two photon or two quanta of radiation and it will form the dimerization reaction, that means dianthracene molecule. So in this case the more than one quanta is absorbed. So here the corresponding Stark-Einstein law is not applicable. Okay, because Stark-Einstein law states that one molecule should react with one photon radiation of energy. Another case, if the corresponding law of photochemical equivalence is not applicable in photo-initiated chain reaction. For example, if the corresponding hydrogen and chlorine, these two gas in presence of sunlight, it will produce the corresponding HCl molecule. So this kind of reaction takes place by the free radical reaction. So when the free radical reaction formation occurs, then or alternatively if the corresponding chain reaction occurs, then in such cases the Stark-Einstein law is not applicable, because in such reaction by absorption of one quanta of energy, large number of molecules get reacted. Okay, so these are the corresponding limitation of Stark-Einstein law. So to overcome the corresponding problem, Einstein later on give the concept of quantum efficiency or quantum yield value. So the concept of quantum yield or quantum efficiency was first introduced by the scientist Einstein, which is an important parameter of a photochemical reaction. Quantum efficiency or quantum yield may be defined as the number of molecules of the substance undergoing photochemical change per quanta or per photon of radiation absorbed. So in this case, theoretically the maximum quantum yield value should be 1, because whatever the number of molecules are there, that the number of molecules should absorb the corresponding photon energy. Alternatively, the quantum yield may be defined as the corresponding number of molecules of the substance undergoing photochemical change per quanta or per photon of radiation absorbed. Or alternatively, the corresponding quantum yield can be defined as the number of moles of the substance undergoing photochemical change per quanta or per Einstein of radiation absorbed. Okay, or it can be defined as the ratio of number of photons emitted by the number of photons absorbed. Okay, so we can write the corresponding quantum efficiency or quantum yield as it is basically designated by phi. So phi is equal to rate of chemical reaction divided by quanta absorbed per second, or we can write in such a way that the corresponding formation of product d of product divided by dt divided by number of quanta absorbed, or in number of quanta absorbed can be written as rate of absorption. Okay, so this is the corresponding definition and mathematical form of quantum efficiency or quantum yield value. Okay, so there are requirement for a molecule which shows quantum yield, means what is the corresponding requirement of the corresponding molecule which exhibit the quantum yield value. So therefore all the reactant molecules present in the ground state should be in same energy state and they are equal reactive in nature. Okay, so molecules in the activated state, because whenever the molecule absorbs the photon energy, then from the ground state it goes to the excited state. So during this kind of transition, molecules in the activated state should be largely unstable and decompose to form the products. Okay, the reactivity of the molecules should be temperature independent. So the question comes that because all of you know that quantum yield, the theoretical value of quantum yield should be unity. So what is the reason behind it? So according to the law of photochemical equilibrium as proposed by Stark and Einstein, each reactant molecule absorbs one quanta in primary process. Hence quantum yield should be unity. But it has been observed that some photochemical reaction in which they show the low quantum yield or high quantum yield. That means it deviates from the unity. Less than 1 value is called as the low quantum yield, whereas greater than 1 is called the high quantum yield value. So for a primary process, since the quantum yield value is always 1, so deviation of quantum yield of unit is due to the secondary process of the chemical reaction, because all of you know that in the secondary process the molecules can be activated, and during the activation some kind of change of the property of the molecule can changes. So the deviation of quantum yield of unity is due to the secondary process. So for that reason, determination of quantum yield helps to understand the nature of secondary process. So you can see here, as I have stated earlier, that quantum yield value is two kinds. One is low quantum yield and another is your high quantum yield. So low quantum yield means when the number of molecule decompose is less than 1 per photon energy, or alternatively in terms of mole you can say when the number of mole decompose is less than 1 per Einstein energy. In such cases the corresponding quantum yield value should be low, whereas in the high quantum yield value, when the corresponding more than 1 molecule decompose per photon energy, or in terms of mole, when more than 1 mole decompose per Einstein energy. In such cases you have observed the high quantum yield value. So the question comes in the mind that what is the reason for the low quantum yield, or in which cases we observe the low quantum yield value. So you can see here, since the excited molecules may lose their energy, because when in the primary process the molecules absorb the photon energy, then it goes ground state to excited state. Once the molecule reaches in your excited state, then what happens? In excited state, the molecule lose their energy by collision with non-excited molecules. Okay, so what happens? That means that excited state becomes somewhat deactivated, since activation would require more energy. As a result, more photon is required to activate the molecule. Okay, because if the correct, you can understand this kind of thing. If in the excited state the molecule lose their energy, then it can be deactivated. So when the molecule deactivate, again the molecule have to be activated. So once the molecule have to be activated, some energy should be provided, and all of you know that energy is in the form of the photon energy. So therefore more photon energy is required to activate the molecule. Alternatively, the total number of molecules remains same, but the total quanta enhances. So lower part is enhances. So obviously the phi value is the number of molecules reacted, that is the fixed one, divided by number of quanta absorbed, that is, since it is enhances, so obviously the quantum yield value should be less than 1. Okay. In the second case, in some condition, molecule may not receive sufficient energy to enable them to product. So in that case, the quantum yield value should be less than 1. That means if the proper frequency of light is not falls on the molecule, then the molecule cannot go to the excited state. So in such condition, the quantum yield value should be less than 1. Okay. Third case is recombination of dissociated fragments will give low quantum yield value, because whenever in the excited state some kind of free radical formation takes place. So when the free radical formation takes place, that means the correct in the excited state the molecule decompose to number of free radical. So suppose H2 can be decomposed as H dot and H dot. Then what happens in the excited state? H dot and H dot, these two free radical combine together. So when they combine together, then what happens? More energy will be required. So when more energy will be required, in such case the corresponding quantum yield value should be less than 1, because externally we have provided the energy, or alternatively we can say in the excited state we have to provide some photon energy. Okay, so in such condition the low quantum yield value can be observed. Next one is what are the corresponding reason for high quantum yield value, because you know the definition of quantum yield. So what happens in the high quantum yield? Absorption of radiations in the primary process produce atoms or free radicals which initiate a series of chain reaction. The product formed in the excited state collide with the second molecule and transfer its energy to the second molecule. Then what happens? Similarly, second molecules get activated in the excited state and then transfer its energy to third molecule. So in this way the parallel chain reaction starts and the number of reacting molecule will be high, but the number of photon energy remains same. Okay, since the number of photon energy remains same, but the number of molecule enhances, because in the chain kind of reaction the corresponding free radical formation, the corresponding chain reaction start. Okay, so in this case the high quantum yield value can be observed, or the corresponding phi value should be greater than 1. The next point is, if in the excited state there is formation of intermediate product which catalyst and enhance the rate of reaction. In such case, the corresponding phi value should be greater than 1. If the reaction is exothermic in nature, then what happens? The heat energy is evolved. So when the heat energy is evolved, corresponding energy value becomes high. Then it basically activates other molecule without the absorption or additional quantum radiation. Then phi value should be greater than 1. So for high quantum yield, if the corresponding reaction is exothermic in nature, then the corresponding heat energy is basically evolved, and they have tendency to activate the other molecules. Okay, but any kind of absorption does not take place, so obviously quantum yield value should be high. But in case of endothermic reaction, the corresponding quantum yield value should be less, because in the endothermic reaction the heat energy is required. So more number of energy, when more number of energy is required but the number of molecules should be same, in such case the low quantum yield value can be observed. Okay, so you just see in the two different kind of example of the photochemical reaction. The first one is the photolysis of chlorine and hydrogen. In the photolysis of chlorine and hydrogen, it will produce hydrogen chloride. So the corresponding reaction can takes place in such way. First, what happens in the primary process? Chlorine absorbs the photon energy and it will form the corresponding chlorine free radical or chlorine atom. Then what happens? Chlorine reacts with the hydrogen, it will form the HCl plus hydrogen. Exothermic reaction, since it is the exothermic reaction, heat is evolved. Then what happens? Then next hydrogen molecule, it reacts with another chlorine molecule, it will produce HCl plus H. So this kind of chain reaction start. So the corresponding number of molecule enhances. So in such case, the corresponding quantum yield value should be high. And it is reported in literature that the photolysis of chlorine and hydrogen, the quantum yield value is around 10 to the power 5. But in the photolysis of bromine and hydrogen, the quantum yield value of HBr is very low, because the main point is that the reaction is endothermic. Endothermic reaction means the heat energy is required. So more number of energy should be provided. Okay, although it is the chain reaction, but here the more number of energy should be provided. That is why number of molecules remain same, but since the more number of photon energy is required, obviously the quantum yield value should be less than 1. So and it is reported in literature the quantum yield value is less than 0.01. Then how can you prove that the photochemical equilibrium constant is directly proportional to the intensity of light absorbed? Because till now we have learned that any kind of photochemical reaction takes place in presence of light. So if you consider a light sensitive reaction and equilibrium reaction, where in the forward is the light sensitive and backward reaction is the dark or thermal sensitive reaction. Okay, so the reaction can be written as A in the forward reaction, that is the light sensitive. That is why when A to B formation takes place, we written as the rate constant value as K1. Whereas in the backward reaction from the product B to the reactant A, since it is the equilibrium reaction, so this kind of reaction can take place dark or thermal condition. Example is the anthracene, because anthracene molecule in presence of light it produces the dianthracene, whereas in the dianthracene in presence of dark it basically regenerate again the anthracene molecule. So this is the corresponding photochemical reaction in which the forward reaction is your light sensitive, whereas in the backward reaction is your dark or thermal sensitive reaction. So in this case, if the corresponding I absorption is the intensity of light absorbed, then the rate of forward reaction you have learned in the chemical kinetics section, the rate of forward reaction should be equal to some rate constant, since the rate constant is K1 into concentration of A. And so how much concentration of A? Because A molecule in presence of photon energy, it converted to the B molecule. So the concentration of A we can written as K1 into I absorption. Okay. Similarly, so rate of the reverse or backward reaction should be the rate constant K inverse 1 into concentration of the product, that means concentration of B. Since I have already stated this kind of reaction is the equilibrium reaction, so at equilibrium rate of forward reaction should be equal to the rate of backward reaction. So I can write K1 into concentration of A is equal to K inverse into concentration of B, or we can write, since the equilibrium constant K is defined as the formation of product divided by formation of reactant equal to small k inverse divided by small k1 equal to I absorption by Cb. That means the corresponding photochemical equilibrium constant is proportional to the intensity of the absorbed light. So since this is the corresponding lecture is made up of entirely on the corresponding education basis, it has no commercial application. Okay, so I have recommended several kind of books. So one is the Rohitagi Mukherjee Fundamental of Photochemistry. The second book in this section I have follow the Puri Sharma Pathania book. So this is the outline, you should read the corresponding books. Thank you for your attention.